Okay, great. Well, thank you for coming again today. We're going to start with a session on fire regimes, climate and fire regimes, and John Keeley will be our first speaker. John is going to be talking about the ever-changing role of climate and weather in Chaparral fire regimes. Again, I think John, like a few of our speakers yesterday, hardly needs an introduction. John is a senior research scientist with the U.S. Geological Survey at the Western Ecological Research Center in Three Rivers. He's also an adjunct professor at UCLA, and John has published, I think, 3,472 papers and 372 books, and has an H index of 7 times 10 to the 6 or something like that. And anyway, I give you John Keeley.
A couple weeks ago, I was at a meeting in Sacramento, and Jerry Brown walked in chewing a cookie, and so I thought, that's a sign of sophistication. I'd try it.
We do have a microphone. John Keeley channeling Jerry Brown. That really scares me. There you go.
And I have to find my talk by myself. Huh?
Oh, I tell you what. Why don't you tell jokes and I'll do it for you? Forgive me.
Well, unlike Jerry Brown, I didn't bring my dog to the meeting. He walked in with his dog following, and his dog was very well behaved.
Oh, geez.
And I should have brought Mike because yesterday was her two-year anniversary or birthday.
And we got a Tuesday thing?
Yep.
Hi, what's on your mind? Speak to this computer. Let's see what it says. I'm always bemused by that. I don't even know what to do when those happen. Okay. Probably.
Is this coming out of my time?
It is. Yeah, I started it already. That's why I'm going so slow. Okay, you're on.
Okay. Thank you. I'm talking about fire, and clearly if the focus of this conference is global change and vulnerability of Chaparral, we can't even begin to approach that without considering fire. Unless you've been asleep for the last 5 or 10 years, you've probably seen headlines in newspapers, something along this line, that global warming is burning down the western US. What I'm going to address are a couple questions. Will anthropogenic climate change alter future fire regimes? And do other global changes pose a bigger threat? Spoiler alert, I'll just tell you the conclusion at this point. If you get tired, you can leave. Evidence to date suggests climate change may not have a significant effect as other global changes in Chaparral, and that doesn't apply to all ecosystems in the West. There's some speculation, and I'll touch on this a little bit, that climate change may impact extreme wind events, but that at this point is really a matter of speculation. But almost certainly climate change will impact post-fire recovery of Chaparral. It will impact type conversion from Chaparral to annual exotic grasslands. And I'm not going to touch on that, but Alex Syphard's talk later will, although I'll be giving that talk as well. Now, 2017 fire season, it was a wake-up call for both managers and scientists. It told scientists that basically there's a lot that we don't know about big fire events in California. The October North Bay, Sonoma, Napa County fires, really significant, not so much for their size, but significant because it represents the greatest losses of lives and property that we've ever seen in California. And so that was a real wake-up call. And then, of course, the fires in Ventura and Santa Barbara County produced the largest modern fire in California history, something over 280,000 acres. So this is sort of a wake-up call. There's a lot we don't know. We saw during these events headlines like, scientists see climate change as being the basis behind these big fire events. Very often these were climatologists as opposed to fire scientists. And during the December fire in Ventura and Santa Barbara counties, the Thomas fire, we saw a number of people reporting that's absolutely unheard of that you get a wildfire in December. But if you study the history of fires in California, you know that's simply not true. We have a record of big fire events in December. December is not all that unique for carrying big fires. Now, one of the reasons people pointed to climate change as being important is that if you looked at the temperature anomalies in a station near where the Thomas Fire. This is the outline of the Thomas Fire. If you go down to the Santa Monica's, where is it? Somewhere around in here is a place called Cheeseboro Canyon that has a RAWS station with about 25 years of data. And if you look at the average over that period of time and compare each year and ask the question, how did it deviate from the long-term average? That's what we call an anomaly. And anything above 0 represents a year where it was warmer than the average, and anything below is it was cooler. And we've broken it out here between winter, spring, summer, and autumn. In 2017, when we had the big fire year, that earlier that year in winter, it was actually much cooler than the long-term average. However, it started heating up, and spring, summer, and autumn were all above the long-term average. And this was some of the data that people used to suggest that global warming may be a factor in driving these big fire events. The thing to keep in mind, though, is temperatures vary a lot from year to year. And the temperature anomaly in December of 2017, when the Thomas Fire occurred, was no greater than temperature anomalies we've had in a lot of years in the last decade. So it was not a unique event, but it certainly provided fuel for meteorologists suggesting climate change was at the root. Now I forgot how to change.
I think enter one of the arrows to the right here at the bottom right.
Don't get up. I don't want people to think you have to show me.
Now my little friend has arrived. We got to get rid of this guy.
Uh-oh.
Is that where you want to be?
Yeah, that's where I want to be. This is data that we've collected over the last couple years, where we've looked at temperatures over the last 100 years on U.S. Forest Service lands, and they vary a lot from year to year. And we've looked at it in winter, here, spring, summer, and fall, and compared different regions in California. This is the northwest portion of the state. This is North Interior, Sierra Nevada, Central Coast, and South Coast. And that's what this is: North Coast, North Interior, Sierra Nevada, Central, and South Coast. And we've asked the question, over the last 100 years, has the amount of fire activity in that year changed in accordance with the temperatures in that year? And what we find is uniformly throughout the state, if you look at just a single variable, and of course, climate-fire interactions are a multivariate phenomenon, but if you look at just one thing, average seasonal temperature, one thing we find consistently is winters are never important in terms of driving fire activity, at least in this type of seasonal analysis. And we see this consistently both on Forest Service lands as well as CAL FIRE lands throughout the state. And that's an important finding, because a lot of the future projections about climate change show that winter temperatures are likely to be when we see the greatest temperature increase in the during this century. And so it doesn't appear to be an important driver. What is really important, though, is spring and summer temperature, and we see that in all the forested lands of Sierra Nevada, North Interior, and North Coast. What we also see is no relationship in the Central Coast and South Coast regions, which are chaparral-dominated landscapes. In other words, climate doesn't seem to be a big driver of fire activity. Now, let me just take two extremes and talk about what we think we know about fire-climate relationships. This is basically the Sierra Nevada region, dominated by forests. This is the South Coast region on CAL FIRE lands, dominated by chaparral. And these represent Hugh's two California fire regimes, the forested landscapes that have missed fires over the last century, and the South Coast, Central Coast region, which has had an excess of fire. If we compare those two regions, we find consistently Sierra Nevada spring and summer temperature really important in terms of determining fire activity that year. We don't see that relation in southern part of the state. We think part of the reason for that is in Southern California, every year it's hot enough and dry enough to burn a large amount of area. And you can see that here. If you look at the summer temperatures in the Sierra Nevada, when it's average temperature around 15 degrees, we have much less area burned than when it's up around 19 degrees average during the summer. If you compare that with Southern California, the lowest temperature on average we get is 19 degrees. So that basically we're always climatically poised for a big fire event. Now, of course, we really, to get at the question of climate and fire, we need to understand all the different variables. We've done a lot of different multiple regression techniques. In general, in the Sierra Nevada, we do see overall there is a significant model. And this is something that's been shown by a lot of investigators throughout the Western US. If you look at forested systems, they do have significant relationship between area burned and climate, and they're commonly called flammability limited systems. Now, Hugh yesterday brought up the idea that these are actually fuel limited systems, but that's really historical. Today, they're no longer limited by fuel. They're because of 100 years of very successful fire suppression, there's plenty of fuels all the time, so that what determines a big year and a low year is their flammability, which is a function of temperature and precipitation. Now, one of the things that's really interesting is if you divide the Sierra Nevada data up between the first 50 years and the second 50 years, we find very different climate models. In the first 50 years, there's precipitation are the important drivers. In the last 50 years, it appears that spring and summer temperatures are the most important variables. So in the Sierra Nevada, we can explain about half the variation from year to year in area burn, just knowing something about temperatures. But one of the important things is that if we're seeing over the last 100 years a change in the fire-climate relationships from one half of the 20th century to the next, we have no way of knowing what the future holds, because these fire-climate relationships certainly could change in the future. Now, when we look at Southern California, overall, we see no significant relationship with any combination of climate parameters. If we break it out into the first 40 years in this case, and the last 50 years, we do see that in the last 50 years, we have come up with a slightly significant climate relationship. It appears, though, to be primarily driven by the prior year precipitation. And prior year precipitation is commonly linked in the Western US to fuel-limited ecosystems, particularly grasslands, because grasslands commonly don't burn during a drought year because they simply don't have enough fuel. And so if you have high precipitation one year, the next year you can get high fire activity. Now, why would you see that in the last 50 years in Southern California? We think it's primarily because in the last 50 years, we've seen significant type conversion from shrublands to grasslands. And so now that's showing up in the fire-climate relationships, and that'll be discussed later in Alex's talk. Now, just to summarize what I think we know about these systems, we can divide the landscape into forested ecosystems, grasslands, and shrublands. And I tend to think that the prominent drivers in these systems are very different. The forests are flammability limited. Not every year is suitable climatically for a big fire event. Grasslands, on the other hand, clearly fuel limited because if they don't have enough grass growth, they simply won't burn. When we get to Chaparral, there's always sufficient fuel, and the climate is always sufficient for carrying a fire. What really drives fire events in this part of the world are humans igniting fires under the worst possible climate conditions. And so we think of those as ignition limited fire regimes. Now, just a few words about what are the big drivers, and we all know what the big drivers are in this part of the world. They're Santa Ana wind events. This is all the fires over 100,000 acres that we've had in Southern California going all the way back to this fire we recreated based on newspaper reports in Orange County. We've had 10 of these big fire events, and most of them occurred during the autumn under Santa Ana wind conditions. Those are the ones in red. And a couple things that are important about these fire events. The number of Santa Ana wind days has changed significantly from one fire to the next. For example, typically we see 2 to 3 days of Santa Ana winds. The biggest fires, though, have occurred when Santa Ana wind events have been much longer. The Matilaha fire in 1932, 5 days of Santa Ana winds. The biggest fire that we have in modern history is this Thomas fire in Ventura County, 10 days of Santa Ana wind events. So the numbers of Santa Ana wind days is critically important. Another factor we think is really important is the amount of antecedent drought. And the two biggest fires on this were the Cedar, or at least modern fires, Cedar and the Thomas fire. And Cedar fire had 54 months of drought prior to that fire event. As you heard yesterday from Steve Davis, the Thomas fire was preceded by 72 months of drought conditions. So extreme drought and extreme wind events appear to be important in terms of driving fire size. Now, one of the things that really raises an interesting question is something that Steve Davis brought up to me at the last meeting where I gave a talk back in February, and he pointed out a paper that I wasn't really aware of, and in which at the time of the Thomas fire, December 4th, 2017, there was this blog, and this climatologist was pointing out that there was something weird going on in the Pacific off California coast, and they called it the ridiculously resilient ridge. And what they predicted is this ridge was likely to last for a couple weeks. And that appears to be an important factor in driving this 10-day Santa Ana wind event. The big question nobody knows at this point is this ridiculously rigid, resistant ridge, is this something that is novel and due to anthropogenic climate change? We simply don't have the answer. It could just be a freak event. Now, we describe these fire regimes in Southern California as ignition limited, and the reason we do is even though we all know the big fire events happen during Santa Ana wind events, knowing there's going to be a Santa Ana wind event does not determine whether or not you get a big fire event. This is the number of Santa Ana wind events every year since 1980, and basically we get Santa Ana winds all the time, but we don't get big fire events. And if you did a regression between the amount of area burned and the number of Santa Ana days each year, you get an R-square of 0.00. In other words, there's no relationship because it is not the presence of Santa Ana winds. They're always present every year. It's somebody igniting a fire, either intentionally or accidentally, during one of these events. And so we tend to think of these as ignition limited events. Now, and this is the way Roger Kennedy, a former National Park Service director, put it, the problem's not fire, it's people in the wrong places. Now, what do we know about ignitions? We're starting to learn more and more. And one of the interesting things about ignitions is ignitions have actually been going down in recent decades. For example, this is arson fires in the northern part of the state, southern part of the state. We've been seeing a decline in arson fires, a decline in debris burning, smoking. So we've been seeing a decline, but not in every ignition source. For example, this is power lines. Power lines have actually in the north been going up in terms of number of ignitions. In the southern part of the state, we see no relationship. In other words, it appears that fire prevention is having a role in reducing some fire ignition sources, certainly not all fire ignition sources. And power lines are particularly critical because they occur during the worst wind conditions. Now, one of the complications in predicting future fire events is this change in vegetation type that we see in association with different fire regimes, what we call type conversion, and I'll talk a little bit more about this when I present Alex's talk a little later because she's not able to come. But one of the things to keep in mind is we see type conversions in lots of vegetation types. We see chaparral converting to grasslands. We see forests converting to chaparral. We're starting to see it in a lot of Western ecosystems. These are pictures that Monica Turner sent me. And this is a lodgepole forest that burned in '88 and then burned a few years ago. And we're starting to see potential type conversion of these lodgepole forests because of this disruption in the fire regime. So in short, if we're going to try and predict the future of fires, we need to recognize that type conversions are something that is going to ultimately change the future of fire on these landscapes. And very often, we don't have a good way of predicting them. The other important complication is fire climate models can change over time. We see that in the Sierra Nevada. Precipitation was important in the early part of the 20th century. Today, temperature is more important. What about tomorrow? We simply don't know. We don't have a good handle on what's going to happen precipitation-wise, which is likely to be an important factor. There's the potential that CO2 could actually increase water use efficiency, but that's a complicated physiological. Okay, I got it now. And then the other thing to keep in mind is when we look at the future, we have to realize that we're likely to see novel ecosystems develop over time, systems that we haven't really anticipated. And this further complicates trying to predict the future. And in fact, some people claim that we ought to expect the future will hold novel ecosystems that we haven't seen in the past. And the other thing is the outcome is going to depend a lot on the order and timing and magnitude of all these different changes. That's another thing we don't have a good handle on. And ultimately, I think at the present, we tend to rely on statistical models. In the future, I think we need to think more mechanistically in terms of how individual ecosystem components will change. So I think I'll summarize it now. And I'll summarize it by just simply saying predicting future fire regimes in Chaparral is not rocket science. It's way more complicated than rocket science. And that's not just a hyperbole. Scientists can predict when a satellite is going to land at a particular point 400,000 miles away. We don't come anywhere close to that sort of predictions. So in conclusion, Max is probably going to jump on me for this because he probably has conclusions, but I would just argue that anyone who says they have a grasp on how climate change will impact future fire regimes, they possess an impressive level of optimism. And anyone who says differently, I would say like Dread Pirate Roberts, you know, they're trying to sell you something. The last thing I'll just leave you with is part of the problem is there's a lot of unknowns. And this is illustrated by the poetry of Donald Rumsfeld back in 2002. And his comments are really best said in the cadence of Dr. Seuss. As we know, there are known knowns. These are things we know we know. There are known unknowns. That is to say, we know there are some things we do not know, but there are also unknown unknowns. The ones we don't know, we don't know. And I'll leave it there.